Good afternoon, everybody. I'm happy to be here today to give this lecture in the Lambda Summer School 2020. My name is Diego Collarana. I work at Fraunhofer IAS. And the title of my talk today is COMET, a contextualized molecule-based matching technique. This is a joint work with Mayesh Tasnim, Damien Gros, and Professor Dr. Maria Esther Vidal. But first, let me give you a brief introduction about Fraunhofer IAS. Fraunhofer Institute for Intelligent Analysis and Information Systems, IIS. It's an innovation center in Germany. We are the leading group of Fraunhofer Gesellschaft in artificial intelligence and machine learning. Currently, we are over 250 data scientists and IT experts, and we solve problems such as data analysis, intelligent linking, and data integration. We have currently opened a new branch in Dresden, the city of Germany, where I'm working right now in this new office, Fraunhofer IIS, and we focus on conversational AI. That means we develop conversational agents and assistants such as chatbots uh, based on knowledge graphs. Currently, we are 15 colleagues, and we have established close collaborations with the local universities such as TUI Dresden. We have as well started to work on different European projects, and we have started to work with our partners in industry, transferring the technology we are building to the enterprises. So let me start with a summary of what we are going to discuss during the talk. And I would present to you this summary with the why, what, and how research framework. This is a way how you can structure and organize your research. So why this topic of entity matching? It's important. Entity matching is an important problem, especially in the big data scenarios, because if you think about it, you have several data sets, several data sources that may contain uh, entities that are referring to the same real world entity. But this information of these entities are spread across several data sets, and you have to find a match. You have to find which of these pieces of information belong to the same entity. But the the similarity between entities is context dependent. And during the talk, we are going to present and to show why taking into account the context while measuring the similarity between entities is relevant and important. So what we have done in this work, we have developed and proposed a technique for matching RDF entities that are the most similar according to a certain context. And how we have done that by modeling the context as a Boolean expression and by using formal concept analysis to create a one-to-one context-aware matching algorithm. We are going now to go deeper into these elements. But let's start understanding what is context. To do that, let's start with these three statements. Barack Obama is the president of the United States. Jon Snow is dead. And the statement number three, downloading copyrighted content is legal. Now the question is, are these statements true or false? Well, that depends. Depends on the context. The statement number one, Barack Obama is the president of the United States. That's true, but in the period from 2009 to 2017. Jon Snow is dead. That is true, according to the book A Dance with the Dragons, the fifth edition. And downloading copyrighted content is legal. It's true in Switzerland for a personal use. So, as we see, the statement it's true or false depending on the context. So context is the situation that limits the validity of information, and contextual information is any kind of description of this situation, according to Bossato. But why is context important when finding similar entities? To understand this, let's take this as example. Let's consider two datasets or two databases. The first system contains data about American politicians. And the second one is the well-known open knowledge graph, DBpedia, which contains all the knowledge from Wikipedia, but as a knowledge graph. So let's say we are looking for similar entities between these two datasets. So in the system, we have information about the former governor of California, Arnold Schwarzenegger, who supports the Republican Party and is a politician. And in the DBpedia knowledge graph, we have information as well about Arnold Schwarzenegger, such as he was the Mr. Universe in 1967, and he played the Terminator, and he's an actor. And we have as well information about the President of the United States, currently is Donald Trump, and supports the Republican Party, and he's a politician as well. So traditional entity matching algorithms will give you as a match uh, the two entities that are the same person, in this case, Arnold Schwarzenegger. But a context-based matching algorithm will give you as a result as a pair of entities, Arnold Schwarzenegger and Donald Trump. Why? Because both are politicians, both support the Republican Party, and both they are former governors in some sort of hierarchy in the United States. But the question is why? Why is this happening? The measure of similarity depends on the context, as I said before. In the context of American politicians, the governor Schwarzenegger is more similar to President Trump than the person who plays the Terminator. So that means the information is relevant or irrelevant with respect to the context. So therefore, context should be considered whenever trying to compute the similarity in an entity matching task. Especially, this is of particular importance in big data scenarios. So we devise COMET to implement this concept of a context-based entity matching technique. But before present the COMET approach in details, let's take a look about the related work. So here I will just mention two approaches that are related to the work we are showing in this presentation. The first one is MINTE. MINTE is a framework for automatically integrate semantically similar entities from heterogeneous data sources. MINTE can use a Jacquard distance or Gades similarity metric as means to identify when two entities are similar or not. On the other hand, LDIF, it's a framework that defines or you can define rules inside the LDIF framework, such as these rules are going to define when two entities are the same or not. The rules can be as simple as comparing two properties or applying more advanced functions and transformations on top of these properties to analyze the entity properties as a whole and identifying which are similar or not. So we have taken MINTE as a baseline to evaluate COMET. Of course, to validate that this approach is relevant and is working properly, we have to compare against something. And in the case of this work, we have taken MINTE as a baseline. So let's now go into the details about the COMET approach. But first, to understand properly the COMET approach, we need to understand a couple of concepts that are used by COMET as foundations. The first concept we need to understand is the concept of RDF molecule. As we have seen in previous presentations, in RDF, you can encode the knowledge of an entity, of any entity, in terms of triples. It means subject, predicate, object. But an RDF molecule in this case means all the property objects that belongs to the same subject. That's the concept of an RDF molecule. To understand better the concept of RDF molecule, let's go back to our motivating example. So let's say we have these three entities, one from the system about American politicians and two from DBpedia. So if we want to represent the information about these three entities as RDF molecules, what we would have to do is to create a small graph that describe the properties and knowledge, for example, of Arnold Schwarzenegger in the system of American politicians, and the properties and objects about Arnold Schwarzenegger and Donald Trump in the Wikipedia. So in this sense, we are converting or transforming the knowledge we have as RDF molecules. The next concept we need to understand is the semantic similarity function. A semantic similarity function in the context of COMET works on a set of RDF molecules. So let's say we have a set of RDF molecules, then a semantic similarity function is defined as follows. It's a function that it's applied between two entities and gives you how similar are these two entities. It gives you a value between 0 and 1. So 0 implies that molecule 1 and molecule 2 are completely dissimilar, and a value of 1 implies that the molecule 1 and the molecule 2 are identical. So COMET makes use of a graph-based similarity metric that is called GADES. The next definition we need to understand is the definition of context. In COMET, context is defined as any Boolean expression which represents the criteria for matching two RDF molecules. For instance, in the case of Arnold Schwarzenegger example, the context of molecule 1 and molecule 2 is going to be true if the occupation is similar. Otherwise, it's going to be false. This is just an example of how we can define the context when two entities need to be similar. So, as I said before, in COMET, the context is modeled as any Boolean expression. The last relevant concept we need to understand as foundation of the COMET approach is formal concept analysis. The formal concept analysis is a methodology for extracting a concept hierarchy from a set of entities and their properties. More specifically, the methodology is based on extracting formal concepts, these boxes you can see here, from a set of entities and their properties. As we can see in the example here, if we have, for example, a set of entities, in this case, animals, and their characteristics here, the formal concept analysis would automatically create a hierarchy of formal concepts where at each level kind of summarizes the entities and the properties that these entities share. For example, we can see here in the box, in the blue box, that dog, cat, rabbit, and donkey share tail and hair characteristics. So this methodology will automatically extract this hierarchy of formal concepts out of a set of entities and their properties. The formal concept analysis can be applied as well to the RDF data model. And in fact, the application of formal concept analysis has a lot of useful and interesting applications in the RDF data model. But how can we apply the formal concept analysis to the RDF data model? If we see in the example, we could organize the most natural way to apply formal concept analysis to the RDF data model would be to organize, for example, the subjects as rows and the predicates as columns, in such a way that the formal concept analysis is going to give us, for example, which subjects share a common property. For example, we can see as a result in the table here in the site that subject 1 and subject 2 share or have the common predicate, that is predicate 2, and the subject 1 and subject 3 have a common predicate, that is the predicate 1 and 2. So these results are going to be automatically analyzed by applying the formal concept analysis on top of RDF datasets. But as well, we can adapt the formal concept analysis methodology to calculate when two molecules share the same context. So as you can see in the example below, as rows, we can define molecules, and as columns, the context that they have. So, such as that formal concept analysis will give us a result when two molecules, for example, molecule 1 and molecule 2, satisfies the condition of sharing the same context, in this case, context 2. Or when molecule 1 and molecule 3 satisfy the conditions that they share the context 1 and context 2 as well. So the goal of COMET then is to find the best match according to the context. So this problem can be defined as follows. So if we have two molecules from two different graphs or data sets, then these two molecules, M1 and M2, are the best contextual match if and only if their context match. It means when they share the same context and when they have the highest similarity value according to the similarity function that we have defined before. Now we can explain the architecture of the COMET approach. As you see here in the picture, the COMET approach receives as input two datasets, a similarity function, and a context expressed as RDF triples. So the first step in the COMET approach is to partition the datasets in a weighted bipartite graph, where in one column we have the RDF molecules from one dataset. In the other column, we have the RDF molecules from the other dataset. And as weights and connections, weighted connections here, we have the similarity, how similar these RDF molecules are according to the similarity function. Then, in the next step, we apply a semantic and context similarity calculator. It means we prune the edges with formal concept analysis and invalidate the ones that does not or do not comply with the context that we have received as input. Finally, in the one-to-one perfect matching calculator, the task in this step is to pick or select the best match between the RDF molecules from both datasets. And as a result, we have a contextually equivalent RDF entities. It means a set of pairs of entities where the two of them are the most similar according to the context and according to the similarity function. So now let's see a bit more into detail how the COMET approach works. So let's consider we have two datasets as the input in COMET, where in the first dataset we have three entities, ABC, which are going to represent the three RDF molecules in the set here we have in the left. And we have other three RDF molecules in dataset 2, which are going to be here in the set on the right. So by applying the similarity function, we can calculate how similar the entities among these two datasets are, and we can create a similarity matrix that each cell here in the table represents how similar, for example, the RDF molecule A is to the RDF molecule 1 from dataset number 2. So as an optional step, we can apply a threshold. It means we can say that we are going to consider only the entities that are similar when the similarity value is bigger, for example, than 0.4. So that means we invalidate or we set to value 0 the similarity between the entities that have lower value than the 0.4. In this case, for example, the molecule C and the molecule 2, their similarity is lower than the threshold, so we convert the similarity value to 0. And finally, by applying the context-aware to apply the context-aware perfect matching, we as well apply the formal concept analysis between the molecules in the dataset number 1 against the molecules in the dataset number 2, and we can as well invalidate, according to the context in this case, the similarities that are not compliant with the context that we have defined it as an input to the COMET approach. So this means, for example, that new similarity values are going to be invalidated, but in this case, according to the context that we have defined. So as a result, we have just three values that represent the one-to-one perfect matching. In this case, saying that the RDF molecule C from dataset 1 is the highest similar entity to the molecule 1 in the dataset number 2. And so, in this way, we find the one-to-one perfect matching. So now let me share with you a summary of the evaluations we have conducted on top of COMET to validate its applicability and its accuracy. So we were interested in answering mainly two questions: whether COMET is able to contextually match entities more accurately than the baseline we have defined. As I said before in the presentation, we have defined MINTE, one of the state-of-the-art approaches to semantically identify entities that are the same real-world entity from two different datasets. And the second research question is about how does the content of the datasets with respect to the context affect the accuracy of comment. Just to expand a bit more on the research question number 2, we have the intuition that the content of the database with regard to the context matters. That means with a higher number of contextually similar molecules among the datasets, COMET has a lesser chance of detecting the correct match. So to answer these two questions, we have prepared 3 different datasets and 3 different configurations of experiments. So in each dataset is divided in as well into datasets, and each dataset contains 1,000 molecules, RDF molecules. And the context is true when molecules between these two datasets share the same occupation. That's the configuration for the experiments. More in detail, for the configuration A, every molecule in the dataset A1 has 2 highly similar molecules in the dataset A2, where one satisfies the context and one does not. That's the gold standard for the experiment 8. For the experiment B, every molecule in B1 has 3 highly similar molecules in B2, where 2 satisfies the context and 1 does not. That's the gold standard for B. And for the experiment C, every molecule in C1 has 4 highly similar molecules in C2, where 2 satisfies the context and 2 does not. That's the gold standard for the experiment C. So once we have defined the experimentation setup, now we can see the results for each configuration. As we can see in the table, COMET performs better than our baseline in every case, in every configuration of the experimentations we have done. So the precision, in terms of the precision and recall, COMET has always higher values. But we can see as well that when we increase the number of contextually similar molecules between the two datasets, the accuracy of COMET decreases as well. This is something it needs improvement, and we can consider this as a future work to investigate and improve the approach. Let me finish this presentation with some conclusions and future work. So I would like you to take these 3 main messages as takeaway of this presentation. The first one is that the problem of entity matching is a common scenario in big data applications. It means that you will have typically the same real-world entity information spread over different and heterogeneous data sources where they will not share any common identity or ID that you can use to merge or to integrate the knowledge of these entities. So you will have to apply entity matching algorithms to identify when 2 entities are similar from different heterogeneous data sources. And to do that, context matters. It means when comparing how similar entities are, the context where you are evaluating the similarity is really important to take into consideration. So in this talk, we have present a novel matching technique where the context is defined as an input and allow us to identify contextually and semantically equivalent entities from 2 different data sources. And finally, we use the formal concept analysis methodology to automatically validate the context among entities from different datasets. The applicability of formal concept analysis is very interesting the topic of automatically analysis of RDF datasets. Of course, there are space for improving the work. So as future work, we have envisioned these points. The first one is to model context as a probabilistic instead of a Boolean expression. That means instead of having just true or false similarity in terms of context, we can have a value between 0 and 1, similar to the value we get by applying or similarity function. We as well would like to expand the one-to-one perfect matching, because we may have some scenarios where there is not always a one-to-one perfect matching between the two data sets. And finally, we would like to explore the scalability and application of the COMET approach on very large big data sets. So that was my presentation. Here you can find some additional references about the topic I have presented today. And yes, I would like to thank you for your attention. I hope the talk was of interest to you, and I'm always open to questions. Thank you.